let's look at a couple examples. Let's say I want to find the, so actually I'm going to phrase this one slightly differently. Let's say I want to use a linear approximation to estimate, what do I got here? Let's say I want to estimate 1.9 to the fourth power times, let's make it interesting. Let me make this out to 0 when I do that. Sorry, I'm just trying to make this not dumb. Sure, times, let's just do cosine of 0.2. There is a homework problem like this. When they say find the tangent plane equation, that means yes, the tangent plane equation and the linearization are literally the same thing. So wait, just so everybody is aware, right, if you want to find the linearization of f of xy at the point x naught, y naught, the equation looks like this. My pens are starting to go. I'm really using new pens. Right, you have the linearization L of xy equals f of x naught, y naught, plus your partial with respect to x evaluated at x naught, y naught, times x minus the x coordinate, plus the partial derivative with respect to y evaluated at x naught, y naught, times y minus 1. This is both the linearization, it's also the equation of the tangent plane. I suppose you might, if you were going to write the equation of the tangent plane, you might write it as z minus z naught equals fx at x naught, y naught times x minus x naught plus fy and x naught, y naught times y minus 1. But they're the same thing, right? So that's how you find the equation of the tangent plane, aka the linearization. So that's what we're going to do here. The only thing here is that, so we're trying to estimate this, we actually have to come up with the function ourselves. So looking at this, I see a number where I'd rather not plug, right? 1.9 to the fourth is hard. The number I want to plug in is actually 2. Similarly, cosine of 0.2, I have no clue. I want to plug in cosine of 0. So what I'm trying to do is I'm trying to say, okay, I'm thinking of my function as, so we're going to let the function of x and y equal x to the fourth times cosine of y. And we are going to linearize this at the point 2, 0. So there is a homework problem like this. I don't remember which number it is. I think it's look here. It's number 19, where they're like use the linear approximation to estimate this thing. The idea there is you have to actually come up with the function yourself. It's not hard. Just take the numbers that look stupid and replace them with variables, and then that's your function. And then the actual nice numbers that those things are close to, that's what we want to actually linearize at. So now we're going to find the linearization. So I'm going to have the L of xy equals f of x naught, y naught. So f of 2, 0 is going to be 2 to the fourth times cosine of 0. Cosine of 0 is 1. So that's going to be 16 times 1. 16 plus, now we're going to find the derivative, the partial with respect to x. So fx, taking the derivative with respect to x, is going to be 4x cubed times cosine of y. And if we plug in the point to 0, we get 4 times 2 cubed times cosine of 0, which is 32 times 1. So for this next part, and let me give myself a little more room. I can make this fit. We're going to get 32 times x minus 2. And then the partial with respect to y is equal to, let's see, x to the fourth is a constant now, times the derivative cosine of y is negative sine of y. And when I plug in the 0.20, I get 2 to the fourth times negative sine of 0. But sine of 0 is 0, so I just get 0. So that's actually not super interesting, but it is what we get. We get 0 times y minus 0. So our linearization at x comma y is 16 plus 32 times x minus 2. We don't get any y's. All right, happens. So then, if I want to then approximate this, I'm trying to see, well, this linearization is an approximation of this function at this point. If I want to approximate this value, I'm going to plug in those values for x and y to see what the function is approximating. So f of 1.9 comma 0.2, which would be 1.9 to the fourth times cosine of 0.2, is approximately equal to L of 1.9 comma 0.2. And then I'm just going to plug in my values. I'm going to get 16 plus 32 times 1.9 minus 2 plus nothing else, right? There is no place to put the y value. That's okay. So I get 16, and then 32 times negative 0.1 is minus 3.2. So I end up with 12.8. Is that close? I have no idea. It should be. Let's take a look and see. We did the calculator, 1.9 to the fourth power times cosine of 0.2. We should be in radians, not degrees. I get 12.77. That's pretty good. Yeah, I feel good about that. So it's actually about equal to 12.77. Cool. So our approximation is quite good. All right. So I should really say, right, these linearization problems, it's kind of the same old thing every time you do it, right? You are taking your function, finding the partials, writing the equation, and then doing the stuff. Let's do one more, and then we will move on. So let's say, sure. Let's look. Yeah. Okay. Let's look at this one. Oh, that's interesting. Okay. Yeah. So. Let's make this one a little bit more complicated. So let's say we want to find the linearization. Let's call it the equation seems fine. Let's say we want to find the equation of the plane tangent to the following. F of x, y is equal to, I don't want to make it too terrible. I don't want to make it too easy either. Sorry, my brain's like, gosh. Let's say e to the 3x times y cubed plus x plus 2 divided by y. Okay, so let's go ahead and find the equation of that change point. Oh, I got to pick a point at the point 0, comma 1. All right, let's do it. So I need to know a few things. I need to know f of 0, 1. I need to know the partial, each partial evaluated at 0, 1. Those are the things we need to know to fill in the formula. So we are going to find f of 0, 1, so plugging 0 for x, 1 for y. We get 1 times 1 plus 0 plus 2 over 1 is 2. So f of 0, 1 is 3. And then the partial is set to x, so the derivative of this is going to be e to the 3x times 3 times y cubed plus the derivative of x plus 2 divided by y is just going to be 1 over y. Right? You don't have to use the quotient rule here. You can just think of this as, oh, I have 1 over, sorry, I should not say that, right? This part here is just 1 over y times x plus 2. And the derivative is 1 over y times the derivative of x plus 2, which is just 1. And then if I plug in 0, 1, so the problem, this notation is not great. You can say this and then you write like a little vertical line to me, you're plugging in 0, 1. So you plug in 0 for x and 1 for y, I get e to the 0 times 3 times 1 plus 1 over 1. So that's going to be 4. Let's do the same thing for y. So fy, take the partial effect y, it's going to be, derivative of this is going to be e to the 3x times 3y squared plus, so now for this, the x plus 2 is the constant. And the derivative of 1 over y, or if you prefer, right, this is y to the negative first times x plus 2. The derivative of y to the negative first is negative y to the negative second. And now we're going to plug in 0, 1. So let's see, plugging in 0 for x, we get e to the 0 times 3 times 1, so 3, plus plugging in 0 for x, we get 2 times negative 1 over 1 squared. So we get 3 minus 2, which is 1. Right, so great, now we can find the linearization, or the equation of tangent plane. I still like to write it as L of xy, but I'll do it differently. So the way I'm going to write it this time is slightly different. I'm going to write it as z minus the z coordinate. Oh, what's the z coordinate? Oh, it's that. It's 3. So z minus 3 equals the slope in the x direction times x minus the x coordinate plus the slope in the y direction times y minus the y coordinate. And if you wanted to isolate z, which you don't have to, but you can, we get z equal to 3 plus 4x plus y minus 1. I will point out, we could do more with this, right? We could write this as, I could even bring everything to the right, and we could write it as like 0 equal to x plus y, 3 minus 1 is 2, it's also a minus z. But you could write it like that, or you could even write it like 4x plus y minus z equals negative 2. This is kind of the standard way to write the equation of a plane. We don't usually do that when we're talking about the tangent plane, aka linearization. And the reason why is because a lot of the time, after you do this, someone's going to be like, okay, now I want you to approximate with your linearization, with your tangent plane, f of negative 0.3 comma 1.2. And not that it's impossible to plug it in here, it's pretty not terrible. But if you notice, if you plug it into this equation, it's really easy to see that, oh yeah, you're getting 4 times the x difference, and you're getting just the y difference here. So this probably is not a great example to show how much easier it is to usually do it this way, but it is usually easier to be like, oh yeah, this thing here, my linearization style looking result is usually the place you want to plug in to find your approximation. So if we did that, we would get that f of negative 0.3 comma 1.2 is approximately 3 plus 4 times negative 0.3 plus 1.2 minus 1, which is going to be 3 minus 1.2 plus 0.2. So that's going to be 2. Interesting. Again, we could check and see if we really want to. It's a little bit hard to plug this in. Let's see. If I actually plug this in, I get e to the negative 0.9 times 1.2 cubed, which I know is 1.728. If you ever want to know why I know that 1.2 cubed is 1.728, there actually is kind of an interesting math story as to why someone would know that weird number. I'm happy to tell you about it sometime. It's not in class if you really care to know. Plus negative 0.3 plus 2 is 1.7 divided by 1.2. And we get 2.119. Pretty good. I feel good about this. So these linearizations, these equations of tangent planes, do allow you to approximate a function at some funky values without having to like actually do crazy or without having to use a calculator, right? We can get a decent approximation with relatively easy arithmetic. So that's about all I have to say about tangent planes. It's kind of the same process over and over and over again. Like trying to wipe the thing off my screen, but it's really just the spot on the board right here. So let's go ahead and move along to the chain rule. So we're all familiar with the chain rule, or I'm not even gonna. We all should be familiar with the chain rule, right? We've done it a lot. We know what it is. But now we're going to talk about the chain rule for multivariable functions. So let's look at this example. I'm not going to talk about how to derive the chain rule or any of that stuff. Not that it's not worth doing, but I feel like you guys are going to benefit more just from seeing like how to do it. So, yeah, let's write. So, okay, here's this example, which is a little bit wordy, but let me say the words to you and I'll write down the important information. The pressure P is for pressure in kilopascals, and the volume and temperature of 1 mole of an ideal gas are related by the ideal gas law. PV equals, I think it's actually PV equals nRT, but I think the person who wrote this problem approximated nR is 8.31, perfectly fine. Okay, so again, this is how the pressure, volume, and temperature of 1 mole of an ideal gas are related by the ideal gas law. If the temperature of the gas is 300 kelvins, the temperature is 300 kelvins, and increasing at a rate of 0.1 kelvins per second. And if the volume is 100 liters and increasing at 0.2 liters per second, then we want to know how fast, or really how is the pressure changing? No, how fast is the pressure changing? And I do think there was one thing, yeah, so like totally physics, chemistry stuff. This is not my cup of tea, really. I mean, I took physics a long time ago at UC Davis. Well, I took the 9 series. Okay. Anyway, physics is fun, but yeah. Anyway, so there was something Dr. Lewis said in class today that I thought was that at least really helped me kind of better understand how these formulas work. So we're interested in finding the rate of change of pressure. So we want to know what dP dt is. The rate of change of pressure, the rate of change of pressure with respect to time. We have an equation for pressure, right? In fact, we need to solve this for pressure. So the pressure equation is, we solve for pressure, it's going to be 8.31 times T over V. Or to make the differentiation a little bit easier, let's actually write it as 8.31 times T times V to the negative first. So P is a function of T and V. And both V and temperature, T, are functions of time. And I'm going to show you kind of how mathematicians usually do this. And then I'm going to talk about some of the meaning, because again, I want to go back, I want to reference back to something that Dr. Lewis said that I thought was really great. So here's here's just how to do it, right? Interpretation aside. P is a function of what variables? Oh, P is a function of temperature and volume. And then temperature and volume both are functions of time. So the way we write down what the derivative of P is with respect to time is we have to find all the pathways from pressure to time. So here's one pathway, here's another. This pen is garbage. along this pathway, to get from P to T, we're finding del P, del T, and it is a del because P is a function of more than one variable, so when we're taking that derivative, it's a partial derivative. And then to get from temperature to time, we're going to do dt d little t, because again, it's a derivative because it's not a multivariable function. And then to get from here to there, you're going to do del P del V and the dv dt. So we get the derivative of P with respect to T, and it is a derivative, not a partial derivative, because P is a function of time, and only that variable when you kind of drive down to it. That's equal to this times this plus this times this. You have to, so each pathway, you multiply all the paths together to, like, you multiply all the steps of your path together, and then you add up all the different pathways you can use to get to from P to T. That's really kind of how it works, no matter how many things you've got. So this is going to be del P del T times dt dt plus del P del V times dv dt. Now, here's what I thought was really kind of interesting about how Dr. Lewis was interpreting this, which is a very valid interpretation. So del P del T is essentially, well, I'm reading it as the rate of change of P with respect to temperature. But another way you could think about it is it's the sensitivity of P to changes in the temperature. And so that's talking about, like, if you know how much the temperature changes, that is going to tell you how much the pressure is changing by multiplying by it. And again, this would be, right, this is the measurement's not my favorite. This is in pascals per Kelvin, right? It's the units of pressure divided by the units of temperature. And then this part here tells us how much the temperature is changing. So if you know how much the temperature is changing, and you know what the sensitivity of P is to changes in temperature, when you multiply those together, that tells you how much the pressure changes. And then the same idea here, right? This is the sensitivity of pressure to changes in volume. This tells you how much the volume is changing. And when you multiply those together, you get the change in volume times the sensitivity of pressure to change in volume, which gives you the change in pressure. So that's actually, so I had never really thought a whole lot about this formula, to be perfectly frank, but it really makes sense. You're like, oh, I want to know how much the pressure is changing. Well, I need to know how much changes in temperature affect the change in pressure and how much changes in volume affect the change in pressure. And each of them are given by these particular formulas. Sensitivity times how much change plus sensitivity times how much change. Cool. So again, you don't have to know the meaning behind it, but in this class, I wouldn't say it's an expectation, but it's kind of the point of taking the 17 series versus like the 16 and the 21 series, is that you're really talking about the biological interpretations of what's happening. So that said, the calculation is still relatively straightforward, meaning that if you can draw this diagram, you can find the derivative of any function using the chain rule. Now, how you write your answer kind of depends on a number of things. So here's what we've got. I know I have the other side up there. I've got P equal to 8.31 times T to the V, T to the first. P of, I can even write it this way. And I also have that T is equal to, oh, so I didn't actually write down what T is the function of time was, but I do know that it's increasing at 0.1 kelvins per second, which means that dt is 0.1 kelvins per second. And similarly, dv dt is, I forgot what I said it was, it's 0.2 liters per second. And then we can use this to say that, all right, dp dt is equal to, so again, the formula before was, it was dp dv, sorry, del p del v. So that, let's write those down here. So del p del v, taking the partial of this with respect to v, and get the constant 8.31 t times the derivative of the v part, which is negative 1 times v to the negative second. And then del p del t is going to be, again, derivative of that with respect to t is actually even easier. It's just 8.31 times v to the negative. So plugging things in into my formula, right? It's del p del t times del dt. The letters are killing me. So it's del p del t, so 8.31 v to the negative first times dt dt, and then plus, sorry, I lost my spot here, del p del v, which is 8.31 t. Sorry, let's just make it a minus. Sure, let's make the minus here. Minus of t v to the negative second times del v del t, dv dt, which is 0.2. And again, let me just label those things so everyone can really see it. Right, this is del p del t. This is dt little t. This is del p del v, and this is dv d little t. So there's your chain rule. And then to answer the question, why are some of them, excellent question, Connie. Well, I'm sorry, I didn't mean to call you out, Connie, but still an excellent question. Why are some of them del while the others are d? So you use a del if it's a partial derivative, meaning if your function is a function of more than one variable, then when you take derivatives of it, you're using partial derivatives. So p is a function of capital T and capital V, meaning it's a multivariable function. When we differentiate it with respect to those variables, we are taking partial derivatives. That's why you have del p del t as a partial and del p del v as a partial. On the other hand, t and v only depend on time, right? We're just asking how this thing is changing as time goes on. They only can change as time changes, so they're only time dependent. So since they only depend on time, when we take their derivatives, you get just straight derivatives, right? They're not partials because they don't depend on more than one variable. So the last part here is we have to plug in what we know. We were told that the volume was 100 liters and the temperature was 300 kelvins. So plugging that in, we get 8.3 times 100 to the negative first times 0.1 minus 8.31 times the temperature, which was 300, times 100 to the negative second times 0.2. And if you do the calculations, you get approximately 0.4155. And the units are units of pressure, which were kilopascals, divided by units of time, which were in seconds. So the pressure is increasing, right, because it's a positive rate of change at approximately 0. I think I missed the 0. Sorry. I missed the negative sign too. Excuse me. Let me fix that. It's actually negative 0.04155. So the pressure is actually decreasing as time goes on at a rate of 0.04155 kilopascals per second. So when you have multivariable functions and those things that they are functions of depend on some other thing, we can use the chain rule to take the derivative and find what we're looking for. Yeah, let's do another example. So let's look at this next function. And we're going to do this one two ways. I'm going to kind of show you why we like the chain rule, maybe. So suppose your function f of x comma y is equal to x to the fourth times e to the sixth y. And we also know that x is cosine of t. Sometimes you'll write x of t, right? X of t. And y is equal to sine of t. So we can do this either way. We can either first just actually plug in sine and cosine, right? We could totally write this is going to give us, so here's the first way, right? F of t, I just plug in cosine for x, so you get cosine to the fourth of t times e to the sixth sine of t. And then we can take the derivative. We got to use the product rule, but that's no big deal. So the derivative is going to be the derivative of cosine to the fourth of t. So that's going to be 4 times my stuff to the third power times the derivative of that stuff, which is negative sine of t. Right? It's just to be sure that everyone's okay with this. This cosine of t to the fourth power, so the derivative is 4 times cosine t to the third times the derivative of cosine t, times e to the sixth sine of t, plus, then we flip, right? We do leave that alone, cosine to the fourth of t, times the derivative of that. The derivative of e to the stuff is e to the stuff times the derivative of that stuff. The derivative of 6 sine of t is 6 cosine of t. I don't really feel a need to do anything more with this. Just to point out, right, this is the product rule, right? If this was, say, like, this pen, go away. If this was capital F and this was capital G, then here is your F prime, G, here's your F. However, we could also use the chain rule. We say, well, look, F depends on X and Y, and X and Y are both functions of T. So I can say, well, F prime of T, or if you prefer, df dt, again, it is a d because F depends on the single variable T at the end, is equal to, well, all the pathways, del F del X times dx dt. Plus del F del Y times dy dt. Okay, let's see what those things are. So looking at this function, del F del X is the partial with respect to X. That's going to be 4x cubed times e to the 6y. I feel like I've made a small mistake there. No, I guess not. Plus, I really feel like there's something. Sorry, let me let my brain think for a moment here. Am I doing something dumb? Oh, a little bit, not a ton. I forgot the dx/dt part. Right? So that part there, that's just my del F del X. And then I need to multiply by dx dt, which is just going to be negative sine of t. Plus del F del Y. So the derivative of this with respect to y is going to be x to the fourth times the derivative of e to the 6y is e to the 6y times 6 times the derivative of y with respect to t, which is going to be the derivative of sine, which is cosine of t. And this is the same, although it looks a little different, right? Because in this answer, you got x's and y's and t's. So if you wanted this to actually be the same as this, you'd have to then plug in what x and y were in terms of t. So you say, oh yeah, if x is cosine, I get 4 times cosine cubed times e to the 6, y is sine, times negative sine, which is exactly what I've got right here. And then here I have cosine to the 4th times e to the 6 sine times 6 times cosine t. So they are the same, they're just written a little differently. The thing what usually happens is like if you're actually trying to evaluate this somewhere, usually it's easier to be like, oh, I'm just going to say, well, if t is something, then cosine of t is whatever, and sine of t is whatever. I'm going to plug those in for x and y. So for example, if I wanted to find like f prime of, let's make it interesting. Let's say f prime of, let's not make it too interesting, James. Let's be a little bit. Sure, let's say I want to find f prime of pi. Then instead of going and being like, I want to plug in cosine here and sine here, I'm saying like, oh, well, I know that x of pi is cosine of pi, which is -1, and sine of pi is y of pi, which is 0. So I know that when I'm plugging in pi for t, I'm plugging in 1 for x, sorry, -1 for x and 0 for y. So in my equation here, I would have the f prime of pi would be 4 times -1 cubed times e to the 0 times sine of 0. Okay, that's boring because it's just, sorry, negative sine of 0, which is all 0. And then I'd have plus 1 to the 4th times e to the 0 times 6 times cosine of pi. Sorry, did I say 1? No, sorry, -1 to the 4th. Still going to be 1. Times cosine of pi, which is going to be -1. So then we would end up getting 1 times 1 times 6 times -1, which is -6. Okay. Holy crap, 1:49 already? Jeez, time just flies by. So let's look at 1 or 2 more examples, and then that'll be it. Let me actually take a quick glance at your homework again, just to see if what I'm about to say really is pertinent or not. I'm just curious here. So I have to admit, looks like all the functions you're looking at where you're using the chain rule are just functions of x and y. There aren't any other weird things on there. It makes me feel like I shouldn't spend time talking about that. So it's probably in your interest. Yeah, I'm going to start talking about the directional derivative for the last 10 minutes here, because it's on your homework, and I imagine some of you would like to get to that before I see you guys on Monday. So it actually has to do with the dot product, with what has to do with the dot product and with the thing we just talked about. So let me show you guys this. It's, yeah, I can fit this in there. Okay, so it's a lot to say. Yeah, we can do it. Okay, so okay, so bear with me. Hold on for a minute. This is going to be kind of a bit much. So just a few reminders. Remember the dot product. If you have the vectors v and u, and the angle between them is theta, then u dot v is equal to the magnitude of u times the magnitude of v times cosine of the angle between them. Cool. Also, if we know how to write, if we can say that like u is the vector, I like to write my vectors like this, AB, and v is the vector, say, CD. Another way of calculating u dot v is by multiplying the components together and adding the results. be A times C plus B times C. Great. And then, yeah. So the idea here is that I want to find the derivative in a direction that's maybe not X or Y. So let's look back at our mountain again. The mountain so the function, yeah, I'll come back to this. Well, that reminds me, I should take a quick screenshot of the attendance. 1 second. Let me close the chat for just a moment. Take a big old screenshot of all of them. There's so many of you guys. It's great. I'm glad you're all here. It just always like blows me up. There's like, holy smokes, there's a lot of students. Grant has like twice as many students in this class. He has like 70 students. It's kind of crazy. So here's the idea. Our mountain, f of x comma y equal to 9 minus x squared minus y squared. And it looks vaguely like this. All right, that's a mountain. And yeah, we can draw the coordinate system. Cool, there's a mountain. And we want to look, we're looking specifically at this level curve when z is equal to 4. And specifically, I want to look at the point 1, 2, 4. That point right there, that's the point 1, 2, 4. And what I'm really interested in is I want to know what the derivative is. So when I say the derivative, I mean the slope of the surface or the slope of the tangent line. What's the slope of the tangent line in the direction of, I'm going to use this direction vector. I'm going to say the direction of v equal to 4/5 comma 3/5 from that point. So notably, this is the positive x direction. This is the positive y direction. So if I'm moving in the 4/5 x direction, 3/5 y direction, I'm definitely moving kind of out and to the left, right? I'm kind of moving out that way. So I'm moving away from the middle of the mountain. So I'm going like down the hill. So I should be expecting to get a negative result. All right. So here's the idea. Let's look at the top view. So here's my level curve where z is equal to 4. And here's the point 1, 2. Right, there's x comma y is 1, 2. And we are interested in traveling in the 4/5, sorry, the 4/5, 3/5 direction. So over 4/5 up 3/5. So we want to know, right, if you move in that direction, so 4/5 out, 3/5 over, so maybe like that. Okay, so if we move in that direction, I didn't really draw that very well. Not the best. Sorry, it's hard to draw this. Basically, I want to know, like, here's my, if we move out that way, I'm trying to think of like, okay, we move that way. I'm really kind of moving like that way. So that's the question we're trying to answer. Okay, here's what we need to do. I need to write the equation of this line, which a line in 3 dimensions is a little bit challenging. So I'm not going to justify this part fully because we're one time, but this line right here, right, that's kind of that's tangent to this surface at that point, that tangent line, I can write this way. It's given by the following. You have to use parametric equations. X equals 1 plus 4/5 t. Y equals 2 plus 3/5 t. Sorry, I should be, yeah. kind of blew it there. Not terribly good. Really, I'm not finding the equation of this line. I'm actually finding the equation of this line. Right, so it's actually, there's no z component, so it's not moving up or down. It's just the line that's yeah. Sorry, my picture, I'm looking at my picture, I'm like, okay, that seems sensible. All right. So here's what we're really, this picture always throws me off. Sorry. We're really just thinking, we're thinking if we move kind of flatly, right? If I move this out, still in the z=4 plane, what happens? Well, if I move out, I'm going to go like down the mountain. All right. So here's what we're going to do. I'm trying to find the rate of change of this function with respect to how t is changing, right? Because this function depends on x and y, but x and y both depend on t. Again, I just want to make sure everyone's okay with this. I know I said I was going to explain. Right, if t is 0, you get the point 1, 2, because you get 1 plus 0 and 2 plus 0. And then if t gets bigger, like if t is 1, you move over 4/5 in the x direction, up 3/5 in the y direction. If t is 2, you move over 4/5 and up 3/5. Right? You just keep doing that. So check this out. df dt, the derivative of f, right, which I'm looking for. I want to know what's the slope of the tangent. I'm going to use the chain rule. It's going to be del f del x times dx dt plus del f del y times dy dt. Now, there's a very particular way of thinking of this. This is equal to the vector del f del x comma del f del y dotted with the vector dx dt dy dt. All right, so here's what this is. This vector here, the vector of partial derivatives in order, is called the gradient of f. And it's actually, we use that for a vector of 2 or 3 or more components. But the gradient of a function f is the vector where each component is the next partial derivative. And then this here, if you look at what we've got, dx dt is just 4/5. dy dt is just 3/5. Oh, that's our direction vector, which I really actually wanted to call u, not v, sorry, because it should be a unit vector. Okay, I know we're like out of time, but here's what I want to say, and we'll finish this. The directional derivative of the function f of xy in the direction of the unit vector u. So if they didn't give you a unit vector, you have to divide by its magnitude to make the unit vector. Is given by, it's written like this, d u f, the directional derivative of f in the direction of u. And the way it's calculated is as the gradient of f evaluated at the point you're interested in times, sorry, not times, dotted with u. So if you're trying to find a directional derivative at a particular point x naught, y naught in the direction of the vector u, this is how you calculate it. So let's do it for this particular problem. It'll just take a second. Hang it. Oh, sorry, I didn't erase that. So hang in there with me. For this particular problem, here's our function. Our partial with respect to x is -2x. Our partial with respect to y is -2y. Our gradient at the point 1, 2 is -2 times 1, -2 times 2, right? It's the partial with respect to x and then the partial with respect to y. And so then the directional derivative of this function in this direction, the direction being 4/5, 3/5, at this point, 1, 2, is this -2, -4 vector. That's your gradient at that point, dotted with this unit vector, 4/5, 3/5. When you dot these two vectors together, you get -2 times 4/5 plus -4 times 3/5, which ends up being -8/5 minus 12/5, which is -20/5, which is -4. So here's what that says. It says that at that point, in that direction, the slope of the line tangent to the surface in that direction has a slope of -4. Okay, I've talked too much, but what I want you, and we'll definitely talk more about this next week, but I wanted to at least give you guys a semblance of how you find the directional derivative in case you wanted to work on your homework over the weekend. This is how you find a directional derivative. You take the gradient evaluated at the point you're interested in, and you dot it with the vector that's in the direction you're interested in taking the derivative in. And if it's not a unit vector, like if they say take the derivative in the direction where it's in the same direction as like v equal to, I don't know, 12/5, then the unit vector you have to use is u equal to 12/5 divided by the magnitude of that vector, which is the square root of 12 squared plus 5 squared. Okay, I really will stop.